Hey everyone, my name is Sanya and today I'll be doing problem number 19 in section 3.3. The problem says to find two linear independent Frobenius series solutions, and problem 19 is 2x second derivative of y minus the first derivative of y minus y equals 0. So how I went about doing this was I followed the example Dr. Soto had on our class page and example 4. So the first step is to divide it by 2x. So you divide it by 2x, and on simplifying it, you write it in such a way that you have y dash by x and y by x squared. Now in order to get this, you would have to multiply and divide by x. So you could get a term which divides by x squared. So in this case, my p is negative half and my q is minus x by 2. Now, if we have to say p of 0, now p of 0 in the case of minus half is going to be minus half because there's no x term, so it wouldn't change. But when x is 0, q of 0 is 0, right? Okay. So we can say that x equals 0 is a regular singular point since both p of x and q of x are analytic. Since px and qx are polynomials, we can say px equals p0 plus p1x plus p2x squared plus p3x cubed plus so on, and qx equals q0 plus q1x plus q2x squared plus q3x cubed plus and so on. So the Frobenius series will converge for all positive x values. The one that we obtain at the end should converge for all positive x values. So our indicial equation is going to be r minus 1 minus half r plus 0 equals 0. And this was the q term, so q0 0, and we have p0 minus half, okay? So this is just basic algebra that I did, and I got r1 equals 3 by 2 and r2 equals 0. And I should choose r1 and r2 in such a way that r1 is greater than r2 and r1 minus r2 is not equal to 0. And this helps when we move on further in the problem to solve the other parts. So using theorem 1, we can say that we have two individual linear solutions that exist. Now y1x, that is when r is equal to 3 by 2, that's r1, we can equate it and say that x 3 by 2 sigma n 0 to infinity a n x raised to n, and a naught is not equal to 0. Like, this is a condition that we're stating that should be true. And similarly for y2x, but since x equals 0, is x not equal, my bad, is raised to 0 because r is 0, we can simplify and say that sigma n 0 to infinity bn x raised to n, and bn is not equal to 0. So by substituting r1 as 3 by 2 and r0, we obtain the recurrence relations below. So we first write the equation as it is, find the first derivative, find the second derivative, and resubstitute this back into the 2x y dash minus y dash minus y equals 0. And this, if you remember, was the question that we had. So the first step is like, it's just basically putting it all back in. So I have 2x and y double dash was this part right here, so I have that in there, minus y dash and minus y. Now the next step that I would do would be to multiply this by x, because I want to get this term to get rid of that, and I want, like, just basically taking this x in and then incorporating it into this so it looks more like this one right here. So once we move that in, we have these two terms that look alike. Now we want to get the sigma terms to be the same. No, before that we try to get even the third term to look alike. So when we do n equals 1 to infinity sigma cn, we can write it as x n plus 1 n plus r minus 1. And so now we see that we have three terms that look alike. And the next step, we want to get even the sigma terms to be the same. So we open it up and we write the first term out and we leave the rest as it is. So we do that for this part and for the second part. So now, as you can see, you'll have a sigma n equals 1 infinity common in all three cases. So we group that all in together and the rest of it comes out. Now we know this should equal 0, and I've taken the condition for n equals 0. So this entire thing strikes off, and then I just have this term that's left out. So shuffling things around and solving it gave me r equals 3 by 2 and 0, and this is what I had before as well. So we can say that a naught and b naught can be any number. So for n, let's take a condition greater than 1. When I placed that in, I simplified it to c n minus 1 by 2n plus r square minus 3 times n plus r. So I did case 1 where r1 equals 3 by 2, and I reduced it to, I placed that in an, I let it be an, and this an, if you see from the previous part, is just the cn equation replaced with an an. So that's simplified out to be a n minus 1 by 2n squared plus 3n. I let a naught equal 1 for the first step, and I just substituted 1, 2, 3, and 4, and these are the values I obtained. So we can put this all back into the y1x and write it out this way, because it's x 3 by 2, that was our r, and 1 plus x 1 by 5 x naught plus 1 by 70 x squared, and it goes on. And my second case was r2 equals 0, and I put that into bn, so it was bn equals bn minus 1, and when you put in 0, that's over here, you get 2n squared minus 3, and that's basically what I have here. And I let b naught equal 1, so I substituted values back into this equation, and I got these values out, and I could put all that into y2x equals, and since I have x raised to 0, that's just 1, so that term didn't matter anymore, and it was just 1 minus my first term minus my second term, third term, fourth term, and so on. And that's how I solved this problem.